So we repeat now everything again, but in this case for the negative tone resist. And I hope that you will be willing to participate a little bit for this round. So now I'm going to ask you, what does it look like when we have the bright field design in optimal conditions? So contact is perfect, and the optimal dose and optimal development for a negative tone resist. So I'm asking, what would this image here look like, right? Do we get a square of resist, or do we get a square hole? Yep. So we get a square hole. And because we are imagining that we are using the non-bleaching N-loft resist, we also get negative sidewalls in this case. Okay? And then what about down here in the dark field design? What do we get there?
The opposite, a square.
A square? And also the opposite on the angle?
No.
In the
Shouldn't it be just straight?
Well, so up here we get the negative sidewall here, right? And then down here we say, okay, we get a square of resist. Does it then have the sidewall out, or in, or straight? What do you say? In. Yes. So the angle is the same, because we didn't change anything when it comes to the cross section. We only changed the pattern, basically, right? So the angle is the same relative to the resist, right? Okay, so what happens then when we go to proximity? So now we introduce an air gap. The air gap makes the light diffract as it leaves the mask. So what happens to the hole in the case of the bright field design? Do we get a smaller hole or a bigger hole?
Smaller.
A smaller hole?
Yeah.
Uh-huh. And what about the sidewalls? Do they become less angled or more angled? Should we have a look? Oh, so the hole is bigger. But that's not what we agreed, right? That's a problem. And we can see that the sidewalls, they seem like they become more angled, right? So it's more negative. But what is making the hole bigger now? Because the light diffracts, so we get more light below the chrome. Why is the hole then bigger? It's actually because of this problem with the negative resist, is that it cross-links, and if it doesn't cross-link enough, then it's eaten by the developer. So in this case, the diffraction makes the light bend below the chrome, but that also means that, this light that goes below the chrome doesn't come from anywhere, right? That actually comes from the light just on the edge. So it means that this light here is now spread over a larger area, so the effective dose is lower. And that means that compared to the perfect case with the contact, the dose on the edge of the structure is lower, which means that when it comes into the developer, it's dissolved. Does it make sense? Not really? So this part just here next to the edge actually receives a lower dose because some of the light disappears in here. Okay? And then when we go to the other case with the dark field design, We do not, as we would expect normally, because of the light coming out here, we would expect a bigger square. But in this case, because the intensity, well, it's probably because the light that disappears under here is not enough to really cross-link. And since it also steals some of the light just here, that makes the square smaller. And it also means that as we go down here, the effective dose is even lower than what we have over there. So that's why we get the increased sidewall angle. Okay, so let's now try to look at the same when we just change the exposure dose. So the bright field design, we are expecting a square hole, a square hole. What happens when we don't expose enough? So the area around the square receives a dose that is too low. That means that it is more vulnerable to the developer. So we would expect that the hole would be bigger, and we would probably also expect that the thickness would be lower, because it could be eating away a little bit during the development. And then the last question is, what happens then to the sidewall angle? Well, the entire thing is weaker, so the angle should be more pronounced. Let's hope that's the case. Yep. So the assumptions were correct. We get a bigger hole, we get possibly a thinner film, and we get a larger angle. Yeah? And if we look at the dark field, smaller square, it's the same effect again. It's basically eaten away by the developer because the dose is too low. And the same thing with the sidewall. They're eaten away even more because the dose is too low. So what about overexposure then? What would happen there?
The bright field should become smaller.
Yeah, okay.
And
The sidewall angle?
that's it. Or more pronounced.
More pronounced like it is there in the underexposed case? Or less? Let's see. So we see that the square, the hole becomes smaller, right? Because we get some, if we really overexpose enough, we would expect that it starts to really cross-link below, right? And it also means that we give the bottom layer a higher dose, because the top gets a higher dose, then that travels down through the resist. So that means that the developer cannot eat so much. So we get a more straight sidewall. And then, very exaggerated, but in the corners we get this effect where even though we are in contact, we still get some diffraction, and this then overlaps as we look in the corners, right, from the two sides. And when we look at the dark field, we see that, so this is again sort of inverse effect, but it's because the light now makes the square that remains bigger. And the same again, that the sidewall angle is lower, so it's more towards the positive or the straight than it was before. Okay, the last one we have is the development time. So if we take the bright field design and we give it a perfect dose, so we expect the hole in the resist pattern layer to be nice square, perfect size, and then we just don't develop enough time, what would happen?
A small film in the hole.
And yeah, so there could be a remaining film in the bottom, yes. And what about the sidewall? What would happen there?
the angle should be less than...
That's a good suggestion. Yeah, so it's actually exactly like you suggested, that we can see a film on the bottom, and also that the angle is less. And this is basically because what happens is that what we are looking at here is that in the center of the square, the resist is not exposed at all. So this would develop easily in the developer. On the edges, it's fully exposed on the top, and almost fully exposed on the bottom. So initially, nothing happens, and then after the development is done there, it starts to do the sidewall angle. So when we don't develop for long enough, we can get, in the extreme case, we get something remaining down there, but in the normal case, maybe, because usually for the negative resist, it's very fast to take away the stuff that was not cross-linked at all, and then it just doesn't have enough time to go all the way out with the negative angle. Okay. And sort of the other way around, the dark field one, the square is perfect. We may have a film on the bottom, and the sidewall is more straight. So what about then now if we develop for too long? What would happen then to the hole that we have in the bright field design case? And maybe
It should become bigger.
Yeah, the angle should become bigger, yeah, because it has more time, so it probably eats more. And then what about the edge up at the top of the hole? We could maybe expect that it would be the same. In the extreme case, it will probably also eat and make it bigger, the gap bigger, right? And it could also eat from the top and make the film thinner. So at least I've tried to illustrate that in that one, right? And then we can see here on the dark field design, slightly smaller square, and again, more pronounced negative sidewall angle. Okay, so that's all the way through the negative. Now let's look at, again, real-life processing. So I did the same as before with the positive tone resist. I just did it with a negative tone. The thickness is about the same. And the only thing that's different here is that there is the post-exposure bake, but it's done actually at the same time in the same equipment. So it's not a big deal. So now let's look again at this is again the mask in bright field and dark field design as before. So in the contact case where everything is optimized, this is my starting point basically. I start here. You can see again, we see nice things. There is the difference, of course, compared to the positive one, which is that now this is actually holes, and this down here is lines. But that's basically the only difference. So let's try to look at what happens if I introduce a 2-micron proximity. The result is very similar to what we had before. Big ones look nice. Smaller ones look completely strange. So again, right, you see an effect. Here you can actually see this, what I was talking about before, that there's only the 2 outmost lines here, right? And everything else has gone away, and this has become a blur. And yeah. So all kinds of funny things can happen when you have proximity. Okay, so let's look at the process window. So again, we just look at the bright field design. So what we get in the optimal case is a set of trenches and some holes. And then I can reduce the dose by, let's say, 20%. It still looks fairly good. We would maybe be expecting that there could be something left in between, right? In the trenches they could be filling up when we go down. But even as I go to 50% underexposure, it's still good. So this one is not as sensitive to underexposure as the positive one was. So let's try in the other direction. Let's see what happens. This is overexposure, 20%, 50%. You can see it with the 50%, we're starting to lose definitely some resolution, right? When they become black like that, they are probably closed. So there is a hole, but it's not all the way down. But again, still good, right? If we were doing 5 or 10, we would be perfect here. 5 or 10 micron structures, right? So let's have a look at what happens with the development time. So keep in mind that the standard, the optimal development time here, what we see down there is actually 30 seconds of development. So this is 15 seconds only, and you can see that the 4 micron structures are still perfectly fine. So the unexposed structures, they really dissolve very fast in this one, right? But we can also see that we may have the case here with the smallest lines here, that it didn't really have time to eat all the way down, right? To dig all the way down in the smallest ones. And if we try the opposite and just develop for twice as long, so this is 1 minute development, you can see it looks really good. I can hardly tell the difference between this one when I look here and that one. So we don't actually have enough resolution in the image to tell us any difference. But then the next question, of course, is what happens to the dark erosion? Do we see any effect on the film when we do the overexposure? And also another thing is what happens to the sidewall angle? So I actually tried to measure all of these. The dark erosion, you can see that we get some kind of dark erosion when we do the overdevelopment, but the dark erosion is actually much higher when we do underexposure. So this is again because we don't have the enough exposure dose. That means that the thickness is eaten away during the development. But another thing which is worth having a look at is that you can see that the sidewall angle here is in the optimal case with 30-second development around 5 degrees, whereas over here when we do 1 minute development, it's 15 degrees instead. So, and this is approximate. It's just to give you an idea. It's a rough measurement. But that also means that you can actually use this to kind of choose between also what is it that you need. We have this resist that pretty much always gives you negative sidewalls, which means that if you want to do lift-off, it's perfect. But if you want to do something that is not lift-off, then maybe this sidewall angle is annoying. But then you can actually start to maybe say, okay, but if I then have my development time at a minimum, I will get the smallest angle. I didn't actually measure the angle up here for the underdevelopment, so I don't know what that one is. But yeah, so there's some things you can do there. And another thing that you can also keep in mind is that if you are doing lift-off, and if maybe the lift-off process is sort of being a little bit problematic, it takes a long time, or some of the structures don't want to lift properly, then you can also use this. So you can do the overdevelopment to get a nice negative sidewall angle, and you can also keep in mind that if the dose is low, then the resist is easily dissolved by the solvent. So that means if you're looking at some optimization or some dose tests that you did, and you have 3 doses that look perfect, choose the lowest one if you're doing lift-off. Because that means it's easier to dissolve it, because the cross-link density will be lower. Okay, I have another one I want to show you here. And don't worry, I won't ask you what this is. But this is something that we actually see from time to time in the clean room. After development, it looks like this. So we have these lines or concentric circles of not fully developed. So there's residues there in between. This is a positive tone resist. So the dark gray areas is the resist. And then of course the question is what's going on. We call it Newton's rings, and I don't know if you know about that experiment. It's a little bit the same as what you can sometimes see in a puddle of rain that has a little bit of petrol or oil on it. You see these changing colors. And that is because the layer, it's a very thin layer, but then the thickness varies across the puddle of water. And that gives you color problems. And this is something similar to it. So it's actually something that changes the dose locally due to interference in a gap between the mask and the substrate, which doesn't have the same dimension everywhere. So you can imagine, so this is probably due to a particle, and the particle is probably out here somewhere in the center of the rings. And it's making like a wedge-shaped gap. So where the particle is, there's no contact. And then far away from the particle, there's contact between the mask. So you have this varying air gap. And then depending on what size the air gap is in relation to the wavelength of the light, you can get anti-reflection effect, because you get the light reflected from the transition from the mask material to the air, and you get it reflected again in the transition from air to the resist. And if they are completely out of phase, these two, then they cancel out, and it's like there's no reflection. And then in the opposite case, when they are completely in phase, they actually superimpose on each other, and it's like there's a double reflection effect. And this is what we see as these lines that are left, that the effective dose is lowered here in these local area. So if we look at the intensity of the exposure light, it will be low here, and it will be high there, and low and high and low and high. And we only see the problem in the low areas, right? Because in between there's normal. So, the solution to this is to increase the exposure dose slightly. I mean, of course, if it is a particle, then it's also cleaning the mask, right? But you could help it by increasing. So this is something that you see this effect when you are exactly on the perfect dose, right? So that means just lowering it a little bit, it becomes underexposure. But if you then move a little bit up into overexposure, lowering it a little bit still works. So that's the solution, right? The immediate solution is just to develop again, because then the dark erosion will take care of the rest of it, and it will be good. Yeah? A little bit for you there, further reading. Microchemicals are the ones that supply most of our resists, and they have a very, very nice homepage with a lot of information on their resists, but also on sort of general processing. And especially they have this lithography troubleshooter, where you can actually look up and say, I did dry etching and now I see bubbles, and then they give you suggestions to what could be going wrong in your lithography process to cause this. And then of course we have our own lab advisor. So here's all the information, all the specific information on the machines. And there is also there's also this very nice page here, which will help you find a starting point on the dose, depending on which resist, which thickness, which aligner you're using, and which developer you're using. So, yeah.